Welcome back to our second session. So now we're going to continue with this particular cases. So our system is like that. So, okay. So this is our system. Now I want to focus on 2x2 systems, but everything I say is true for the general case. So we assume that there is a steady state, there is a fixed point of phi, okay? And we want to linearize our model around this steady state. So after that linearization, we find that A matrix, so A is 2x2 and B is 2x1, okay? Now, obviously we are interested in the eigenvalues of this. So these eigenvalues, as you know, are going to be found through the characteristic equation. So you have the trace, right? The trace plus minus trace squared minus 4 times determinant divided by 2, right? So we know this. Now the idea is this. Lambda 1, 2 will be complex numbers if trace squared is less than 4 times determinant A, and they will be real otherwise. Okay? Now we're going to look at these cases separately. Okay? So first, let's assume that trace squared is strictly greater than 4 times the determinant. Okay? Now this is the case for real eigenvalues that are different. Okay? Now in that case, we have the following result. So it will be a saddle. It will be a saddle if we have something like this. Lambda 1 less than 1 and lambda 2 greater than 1. Okay? So depending on the sign, of course, you can write this in this way, lambda 2 less than minus 1, or here lambda 2 greater than 1, and sorry, lambda 1 greater than 1, and lambda 2 is less than 1. Okay, so okay, let me be specific. So this is an OR condition. So these are, imagine these are statements, okay? Because, and here you have AND, okay? So in saddle, as you know, from one manifold, it will be stable. From the other manifold, it will be unstable, okay? So from one manifold, so this is the stable manifold, and this is the unstable manifold. Here, this could be the, you know, lambda 1 could be greater than 1, and in this case, you will have this, okay? Now, it will be unstable node, okay, if you have lambda 1 greater than 1, lambda 2 greater than 1, okay? Again, this is just a statement. as a whole. So this is an end condition. Okay. Oops. So this is an end condition. All right. So lambda 1 greater than 1, lambda 2 greater than 1. And then, of course, it will be a stable node, right? If you have lambda 1 less than 1 and lambda 2 less than 1. All right. Now be careful, because now the modulus of lambda 1 is equal to lambda 1 in absolute value, right? Right? Because it is just real, as you see. Lambda 1 is real, lambda 2 is real, and these are two different numbers. So their absolute value become the modulus, okay? And these are the results: settle, unstable node, and stable node, okay? Now, if the trace squared is exactly equal to 4 times determinant A, right? Now, in this case, lambda 1 and lambda 2 are equal, right? These are repeated real roots, and they are equal to this, okay? So let's call this lambda, okay? Now, in that case, this is called focus, okay? Focus. And so this is the name of the equilibrium, all right? And we have this. If lambda is less than 1, it is stable. If the absolute value of lambda is less than 1, it's stable. If the absolute value of lambda is greater than or equal to 1, then it is unstable. Okay? So finally, so that's very simple, because now the square of the trace is equal to 4 times determinant. So this is the repeated real case. You have lambda equal half of the trace, and if it is less than the in absolute value, if it is less than unity, then it is stable. Now finally, we have the complex cases. Okay, so the square of the trace is strictly less than 4 times the determinant. Okay, then our lambdas are like this. Okay. Okay. So then we're gonna have what? We're gonna have a stable spiral or an unstable spiral. Okay. So in that case, we're gonna look at directly the determinant. Okay. If the determinant is less than unity, it is stable. If the determinant is greater than unity, it is unstable. Obviously, if the determinant is equal to 1, we will have a center, stable and unstable forces cancel out each other, and we're going to have a center type equilibrium. Okay. So this is how we do it in discrete time dynamical systems. It is slightly different because stability now is about the magnitude about the eigenvalue. All right. In the continuous time case, it is about the sign. Here, sign gives us the, especially in the spiral case, whether the oscillation is clockwise or counterclockwise. So these details are in the textbook, so I do not have time to go into that detail, but it is explained there. So if you want to, anyhow, if you need to use these things in your research, then of course you must have a much more profound understanding of these issues, so that you know, you clearly studied such dynamics. So there's someone in chat, I guess. Okay, Osan writes there's a problem with his connection. All right, so now I'm going to give you a couple of further examples so that you can work on. These will be simply linear models. If you do not have any question or anything to add about this stuff, so it's very simple. Once again, you're gonna, if you want to talk about just stability but not the type of the equilibrium, you just look at the modulus of eigenvalue or the moduli of all eigenvalues, and requiring that their moduli is less than 1. Or you're going to tell me by looking at the trace and the determinant, and then looking at the absolute values of these eigenvalues, and tell me it's saddle path or node or spiral or center or focus, whatever they are. Okay. So let me give you one very simple example first, and then I will give you a 3x3 system. So again, this is example. So just work it out, work on it. So the system is xt plus 1 equals 3 plus 6xt minus 0.1 yt, and yt plus 1 equals minus 0.1 xt plus 2 yt minus 5. Okay. So obviously, let me just solve it. So A matrix is 6 minus 0.1 minus 0.1, 2, right? So your system is xt plus 1 yt plus 1 equals A times xt yt plus you have 3 here and minus 1 here. Okay, so the trace is what? 6 plus 2, it is equal to 8, and the determinant is what? 12 minus minus 1 minus 1, so it is 11 point what, 99? Yeah. So what do you have? The square of trace, which is 64, right, is greater than, strictly greater than the determinant. Then you're gonna find lambda 1, lambda 2, and then you're gonna tell me whether the system is stable or not. Okay. Another example is a macro example. This is a simple macro model. So first we start with some sort of a Phillips curve. Okay. I'm going to define the variables in a moment. Then we have the evolution. So, okay. So let's look at the first equation. In the first equation, we have the inflation rate. Okay, so this is inflation rate. Inflation rate is negatively related with unemployment. So here alpha beta, lambda, and theta are all positive. Okay, so inflation is negatively related with unemployment. So this is unemployment rate. It is positively related with inflation expectations. So this is expected inflation rate. And E here is the exchange rate, okay? Or depreciation of the exchange rate if you want to look at the model in terms of changes, okay? It doesn't really matter. So then we have the evolution of price expectations or inflation expectations, to be more specific. So there's a kappa parameter here, and it is that. So kappa is also positive. All right. So what does it tell you? It tells you that if actual inflation is larger than your expectation, then you believe it will be increasing. Okay, so you increase your expectations. So it is like an adaptive expectations hypothesis. So the evolution of the exchange rate or the depreciation of the exchange rate, again, doesn't really a big deal, has this set up. So once again, all parameters are positive. So gamma, delta, positive. Rho is also positive. Okay. So what's going on here? So there's a persistence in the evolution of the exchange rate, and also if inflation expectations get larger, then people, let's say people, put a higher risk premium for this economy. Their expectations for the future gets worsened. They think so. So you may imagine that this is an emerging market economy which is vulnerable to boom bust cycles. So higher inflation expectations imply higher depreciation, let's say. Okay, and finally, you have the evolution of unemployment rate, and here it is in the short run, depending on the demand management policies. Here we are going to look at the monetary policy simply. Okay, so if the monetary, so mu is the monetary growth rate. Okay, if the monetary authority increases the the growth rate of money supply larger than the actual inflation rate, then this creates a monetary expansion, and through that monetary expansion, a great demand curve shifts right. So that increases output in the short run, and this is, of course, occurring along with a decrease in the unemployment rate. Okay, so again, we have positive parameters here, psi and mu positive. All right. Now, if you eliminate actual inflation rate from the system, because this equation is static, as you see, right? It is not a dynamic equation, but the other equations, this one and this one, depend on that. So you create a system of expected inflation, the depreciation of the exchange rate, and unemployment rate. Oops. Okay. Now, then you will have this matrix. Okay. Then you have that, and that. Okay. And then you have some constants here again. So you want to write these terms here in terms of parameters after eliminating inflation rate, the rate of inflation from the model. Then you will have a very simple linear model. Then you can look at the trace and the determinant and the eigenvalues again. First, of course, you're going to look at a steady state. So a steady state, for instance, I mean, if you look at it carefully, for instance, you have U star equals U star minus C mu pi star, right? So from this, you realize that in steady state of such an economy, inflation rate is equal to monetary growth rate, okay? Or if you look at this equation, for instance, this one, you're gonna realize E star is gamma plus rho E star plus delta pi E star, okay? Steady state value of the uh, inflation expectations. So this is expected inflation rate. But now from this equation, you realize that for this to be in equilibrium, they must be equal, right? So P star E must be equal to P star, and that is also equal to mu. So you're gonna do that that type of logic. Eventually, you realize there could be a steady state, but for stability, you just check. I haven't, but we require these to be between 0 and 1. Okay? Rho and lambda. Rho is here, and lambda is here. So these are, if these parameters are less than 1, I believe, I haven't checked, but I believe if these satisfy these constraints, then you will have a stable steady state. Okay? So there's one last thing I just want to show you about discrete time systems. Then I will be done. Where is it? Where is it? I'm gonna just find it. Yeah. So is there any question about this? So this is just an example, but just work it on. All right. So work on this problem. Write this matrix and find the conditions on parameters. Okay, that would imply stability of the macro equilibrium. Okay. All right. So the last thing I want to discuss is this. So up to this point for discrete time models, so remember in discrete time, time is defined as an element in history, and history is taken as a subset of the set of integers. So this could be any subset of the set of integers. And we looked at a multidimensional system such as this one, where phi is some function from Rn to Rn, or you can define a subset of Rn, and you can still talk about this vector valued function. Now, this system, as you see, does not depend on time. Okay, because this function phi does not depend on time. So such systems are called autonomous. Okay, such systems are called autonomous. Now let me show you a non-autonomous system. In general, this function could be depending on t, or if you want to be more specific, you can still write this. Okay. So as you see, this function now and this function now depends also on time. So such systems are called non-autonomous. Okay, and there's a way to make non-autonomous systems autonomous, because it is difficult to study such systems steady states, right? Because time can go to positive infinity, right? So if if t goes to positive infinity, then it is very difficult to study the dynamics in this way. So what we're going to do? So usually we're going to define a new variable, right? So let me just show you. So let's say I have phi xt plus ht, all right? So now, for the sake of the example, let's suppose that ht is alpha t squared, all right? And alpha is some real number here, all right? So now we define a new variable, okay? Now, by the way, suppose that this is just a number. So here phi is from R to R. Okay, so I have X. This is just one variable. Now I define YT as HT. Okay, so YT becomes alpha T squared. Then YT plus 1 becomes what? It is alpha T plus 1 squared, right? Or alpha T squared plus 2T plus 1, right? So if you write it even more specifically, you have alpha t squared plus 2 alpha t plus 1. Now, in your system, in your original equation, you have now xt plus 1, phi xt plus yt, right? And you want to associate now yt with either xt or yt itself, right? To make a dynamical system. Now, yt, how do you associate yt plus 1 with yt? As you see, you have yt here, right? Alpha t squared. So your system is now yt plus 1 equals yt, this one, plus 2 alpha t1. Now, is this system autonomous or not? I'm asking you. If you follow the lecture, just tell me whether this system is autonomous or non-autonomous.
Non-autonomous.
It is non-autonomous. Why? Because now you have this term. Again, it depends on t. Now, what you're going to do, you define a new variable. Okay, let me use this space. Now you define a new variable, zt, as 2 alpha t plus 1. Okay? Then what happens? You have zt plus 1 equals 2 alpha t plus 1 plus 1, right? So you have 2 alpha t plus 2 alpha plus 1.
Hocam, bu YT plus 1 kısmında bir yerine alfa olması gerekmiyor mu?
Exactly. Thank you very much. That's alpha. So that's alpha, that's alpha, that's alpha, right? So we have 2 alpha t plus 3 alpha. Okay? Now the system becomes, be careful. So this is zt plus 1, zt plus 1, right? So our system becomes, let's change colors, xt plus 1, phi xt plus yt, yt plus 1 equals yt plus zt, right? And zt plus 1 equals zt plus 2 alpha, right? Because 2 alpha t plus alpha is zt, and now you also have 2 alpha, so this is zt. Okay, now your system, as you see, is autonomous, right? So initially you had only one equation. Okay, so this was one equation because we defined it from R to R, right? This was just X, but it was a non-autonomous system. and it was a square term, this h function. Now we try to make this autonomous by defining this new variable and understanding the dynamics of it. But we realized the extended system is still non-autonomous. So we define another variable to make it finally autonomous. Okay. This would help you a lot in practice because many interesting dynamical systems are non-autonomous. Okay. So that was the last thing I want to show you about discrete time dynamical systems. Okay, my friends. Now I can answer your questions. I can I can cover some of the unclear parts. I can re-explain again, so on and so forth. Okay.
Why we convert to unautonomous system to autonomous system?
Well, because it is difficult to apply the original tools that we studied so far in the last 2 weeks when t is a variable there, because t is always increasing, right? T, I mean, in a model with an infinite horizon, t is always increasing. There is no steady state there, so you cannot study it. You see my point?
Okay, yeah, I see.
Yeah,
I get it.
so to apply the so there's some technical discussion there. So we want to define our systems as a you know, as a never mind. That might confuse you. That type of discussion. If you are interested in it, just check the textbook by Oded Galor. So he explains. So there is this concept of diffeomorphism, etc. So he explains such stuff. That may confuse you, but usually when we have a non-autonomous system to apply, you know, to find the steady state, to apply the linearization and the dynamic stability analysis, etc., we want to convert it to an autonomous system that has a steady state. Okay.
Okay.
Okay. By the way, let me also tell you this. So the last system we just developed, this one, as you see, it is not stationary, right? Because if alpha is positive, z is always growing, okay? Z is always growing. If z is always growing, y is always growing, okay? So after that, you may want to normalize this model as well. So there are growing variables, okay? So I will show you this when I show you balanced growth example, okay? When we get to that point in dynamic programming, I will show you a balanced growth model, a model of growth where some variables perpetually grow, but their ratios go to constants, okay? And you will see that. Okay. So our next and final topic will be dynamic programming. In other words, it will be dynamic optimization in discrete time, okay? Next week, we're gonna start studying that. What I want you to do is to look at the first chapter of Stocky, Lucas, and Prescott. Okay? Just the first, okay. Just the first chapter. Just read it. It's a very nice read. Some parts you may not entirely grasp it, but just read it and try to understand the logic of what we are gonna do in the next couple of weeks. All right. So that first chapter is really a good read. Okay. And then I will show you formally how do we define such problems, how do we approach such problems, and how do we try to solve them. Okay.
Okay.
All right. If you have no question, that's all for today from me.
I don't.
All right then. Bye-bye. I'm ending the session.
Thank you. See you.
Take care.
Thank you.
See you next week.
See you.